Hi everyone, my name is Shutai Ma. Today I'm going to present SimulMT to SimulST, adapting simultaneous text translation to end-to-end simultaneous speech translation. This work was done by Shutai Ma, Juan Pino, and Philip Kun. First of all, I'd like to have a brief introduction on simultaneous speech translation. Simultaneous speech translation is a task focused on starting translation before the speaker finishes the speech. It can apply to many applications, such as live video translation or real-time language interpretation. In this paper, we focus on end-to-end approach, which means that we directly map the speech to the text. This approach typically gives us better inference speed and fewer compounding errors compared with the cascade models. There are actually many works on simultaneous text translation, while very few on the simultaneous speech translations. So in this paper, we are going to explore the challenges and the potential solutions to adapt those developed simultaneous text translation techniques to simultaneous speech translation. So there are several challenges for the adaptation. The first one is that encoder states in the speech model are too granular compared with the text models. For example, for each speech input feature, it only covers 10 milliseconds of speech, while for a single word, typically covers 3 milliseconds of speech. It means that the speech model takes longer inputs than text model, so that the computational time is no longer negligible. However, in the text simultaneous translation, we typically assume that the computational time is zero, which is not very practical. The second challenge is that encoder states in the speech model are more continuous compared with text model. In the text model, each encoder state is corresponding to each individual token, so that state is more discrete. So for the speech translation, we found that a simultaneous policy for text models are not able to reach the expected performance for the speech translation task. Next thing is I'd like to mention the latency evaluation, which is another factor to evaluate besides the quality. So we first extend average lagging for the speech task, which was originally proposed for the text translation task. So there's two parts in average lagging. The first part is the dy here, which is the delay that generates the word yi. The second part is the oracle delay, or the delay for the oracle system, which is the best that you can achieve to generate the yi. So the average lagging is basically the average difference between those two parts. For the text translation, those two parts are measured by the number of input tokens. So in this paper, for the speech task, we use the duration of the speech to measure the delay. After we extend average lagging to speech, we also consider the computational time for the latency evaluation. Thus, we propose computational weighted average lagging. So we simply just let the dy to be the real time that's spent to generate the word yi. So here is a general architecture for a simultaneous text translation model. During the decoding process, there is a simultaneous policy. It takes current input and current prediction and predict action of whether to predict a new token on the target side, which is the write action, or to take a new source token on the source side, which is the read action. Due to the unique characteristics of the speech translation that we mentioned before, directly applying this architecture to the speech translation is not working that well. Therefore, we propose the predecision module, which is an encoder-only module that decides whether to start a simultaneous decision-making process. Equivalently, it just group a, a chunk of state as input for simultaneous policy. Theoretically, there's two types of prediction module. The first type is fixed prediction module. That means we just make a simultaneous decision at every certain number of states. The second type is flexible prediction, which means that we use a separate policy on the encoder side. For example, we can predict the word boundaries and use that for the prediction module. This idea actually was adopted by the Van et al. 2020, which is a contemporary work of ours. After the prediction module, we explored the simultaneous policies for speech translation. So those two policies are already developed in the text translation. The first one is the WaitK policy, which is a fixed policy that with k steps of input and then read and write alternatively. The second policy is monotonic multi-head attention, as known as MMA, which is a flexible policy that extends the monotonic attention on the transformer models. So here is our experimental setup. We work on the English-German part of the master-C dataset. All our model was developed on the S transformer, which was introduced by the Diganji et al. 2019. As to the data preprocessing, on the source side for speech, we use log-mail filter bank features extracted from 25 millisecond sliding windows with 10 millisecond step size. On the target side for text, we use 10,000 unigram vocabulary from the toolkit sentence piece. For the flexible prediction module, we actually use an oracle word boundary generated by Gentle. The reason for that is we just want to know whether a perfect flexible prediction module will improve the overall performance. Van et al. 2020 had the same idea about the word boundary, but they trained a separate ASR model to predict the boundaries. Unfortunately, we are not able to compare their work because we're using different latency evaluation metrics. Okay, next thing we'd like to see what's the performance of this 2x2 combination. So here is the qualitative latency trade-off for 4 settings. We can see the best setting is that we use a flexible prediction module and a flexible simultaneous policy, which is MMA. So when we look deeper into the simultaneous policy, we found that WaitK and MMA is very close to each other, which is actually very different from the text translation task. In the text translation task, actually the story is totally different. The MMA is way better than the WaitK. So from this observation, we can see that the flexible policy is harder to learn on the speech task because the speech set is more continuous. We then look deeper into the prediction module. We first look at the flexible prediction with oracle word boundary, which is marked as purple dots here. We found that for the flexible policy, it actually has some improvement. However, for the fixed policy, there's no significant improvement. If we look deeper into the fixed prediction module, we can find that for the fixed simultaneous policy, the performance vary a lot, depends on the step size that we take for the prediction module. Well, for the flexible simultaneous policy, it's more robust to the prediction module. We next take the computational time into consideration. We found that some policy ideally has very good latency, but in practice, they are not very usable because very high computational time. For example, the red triangle here represents the fixed prediction module with a step size of 200 milliseconds and a wait key policy. Ideally, it has a pretty good latency, but when considering the computational time, the latency just increased significantly, which can be hardly used for practice. Therefore, we encourage the future work to use computation-aware latency for a more realistic evaluation. Here are the conclusions. We investigated how simultaneous text translation methods can be adapted to end-to-end simultaneous speech translation. We introduced the concept of prediction module. We adapt average lagging to be computation aware. We carried out a series of ablation studies to address the challenges and the potential solution for the simultaneous speech translation. Thank you so much.